Hello, everyone. We are now live. Thank you very much for joining us today on the 29th of September. My name is Matthew, and I'm one of the course staff for the online course on Coursera and Udemy. Alexander, as always, helps us with behind the scenes stuff, Alexander Danahy. And Professor Impey, why don't you go ahead and welcome everyone, and we'll get started with questions.
Okay, so welcome to you all for questions to do with the online courses, and floor is open for your questions.
Excellent. Thank you very much. The first question is from Sudhanva. What is your opinion on multiple water bodies found on Mars via Marsis? I'm not familiar with Marsis, but what is the current state of water on Mars?
The current state is that the surface, of course, has no water and can't have water. The pressure is too low and the temperature is too low for liquid water to exist. So the questions revolve around whether there's liquid water under the surface. And that's actually hard to measure. There's definitely a large amount of frozen water, ice, under the surface. So mid-latitude glaciers were found by Mars orbiting instruments years ago, and there's current orbiters are accentuating that evidence and getting higher resolution radar imaging. Radar can let you see below the surface and detect water by the way the reflectance of it. Finding liquid water is much harder. Proving it's liquid is harder, and in fact liquid water probably only exists in localized regions, subsurface aquifers, which we have indirect evidence that they exist from other imaging experiments that show the scars on the surface of aquifers erupting through a rocky escarpment and sending liquid water, which then evaporates quickly and freezes down a hillside. So we know that there's liquid water under Mars, but it's very localized and it's probably very small total amounts. But the total inventory of water on Mars, if you take all the mid-latitude imaging together, is that if you could take all that frozen water, liquefy it, and spread it around the Mars, it's about 4 centimeters worth of water on the whole planet, which is quite impressive. That's actually a non-trivial amount of water. So that's the inventory of water on Mars. But probably a very small fraction of that anywhere under the surface is in currently liquid form.
Thank you very much. The next question is from Jahidul, who is on with us live. Professor, what is your opinion about the moon landing? Some people say it's fake and some people say it's correct, but I seem to feel some confusion. What should we believe and why?
Right. So in the United States and less so elsewhere in the world, there's a persistent conspiracy theory that holds that we never went to the moon. And it's based on sort of tropes or pieces of supposed evidence that pass around the internet and are endlessly propagated and sometimes altered. Now remember, digital imaging can be altered so easily. So part of it reflects there's claims that the shadows were implausible or impossible on some of the photographs that the astronauts took. There were claims that the flag was doing something strange that was also impossible. Remember, there's no atmosphere on the moon. The flag that they planted in the ground was held rigid by rods that were attached to it. But basically, it's a laughable conspiracy theory. It really is. It's hard to imagine that an enterprise, the Apollo moon landings that involved hundreds of thousands of people, and the direct part of which involved hundreds of people in NASA centers, would have been faked. And then there's the small matter of the 24 people that went to the moon, half of whom stood on the surface. Okay, they're part of the conspiracy, fine. So you have to paint such an outrageous picture of a crazy level conspiracy and secrecy when there's massive evidence against it that I just find it a humorous conspiracy. I literally do not take it seriously. If you wanted to slam dunk or cement the fact that it happened, we can see the hardware that the astronauts left behind on the moon with telescopes from the Earth or imaging from the Earth. There were instruments left on the moon, including reflectors and magnetometers that give us current measurement lunar geology and the distance to the moon accurate to millimeters that we know. Therefore, we know the moon is slowly getting further away from the Earth. So we're doing scientific experiments and have been since for 50 years with instruments left on the moon. So that is one of the conspiracy theories, that it is so leaky it doesn't even hold a teeny bit of water.
All right, the next question is from World of Science, who is interested in fusion. And there was recently a story about NASA finding a way to generate energy using fusion. So could you talk about sort of the current state of fusion, and is there any possibility of us building a fission-fusion cycle that exists in the sun in the near future?
Fusion research has been frustrating because it's been going for half a century essentially, and has made very slow progress. And basically, until recently, having a prototype fusion reactor that could attain what we would call break-even, which is where the energy generated from fusion reactions matches the energy required to create those conditions. In other words, you get net energy out, could only be done for fractions of a second, basically, not for any length of time at all. So that's obviously not a viable reactor. It does, however, demonstrate that we do have technologies to create the conditions on the Earth that would allow fusion to occur. The fundamental problem is that the temperature required for fusion, millions of kelvins, is of course enough to vaporize any container made of any substance we can imagine. And so the plasma where the fusion is taking place has to be retained magnetically or electromagnetically. And that's a big challenge. For decades, there was a standard prototype design that was played out in the US, Europe, and Japan called the tokamak, and that was a toroidal magnetic containment device for the fusion. Progress was very slow. There have been recent stories about designs for smaller scale fusion reactors that don't use that tokamak design that goes back to the 60s and 70s. Uses different geometries, different containment mechanisms, still fundamentally electromagnetic, however, and where the power requirements to create those conditions are moderated. So there are new designs on the table that are much smaller prototype reactors, actually, where the break-even point seems like it will be easier to achieve. But at the moment, they have not demonstrated that. So fusion, commercial fusion and practical fusion power appears somewhat closer than it did a few years ago. There has been progress recently, but we're nowhere near the equivalent of a fission reactor. Fission reactors, of course, produce 10% maybe of the world's energy, so that's been around for a long time.
The next question is from one of our live viewers. Chavi would like to know, how do gamma-ray bursts work? How are they produced, and how common are they?
The gamma-ray burst phenomenon has been known for a couple of decades, since the Compton GammaRay Observatory went up, and then other gamma-ray observatories noticed these flashes of gamma rays. Gamma rays, of course, don't penetrate the Earth's atmosphere, so this work can only be done from space. And there have been a series now of gamma-ray observatories. And essentially, once a day, somewhere in the universe, a stellar cataclysm produces a gamma-ray burst, which in the moment of the gamma-ray burst outshines the entire universe, the rest of the universe, in gamma rays. That's the spectacular take-home message of a gamma-ray burst. Since then, we've now found hundreds and then eventually thousands of gamma-ray bursts. They're evanescent. They last a very short time. There are different categories of bursts. There are so-called long and short bursts. The short bursts are fractions of a second. The long bursts have a peak and then a tail that can last 5 or 10 seconds. They seem to have different originations, but in each case, the gamma-ray burst is a stellar cataclysm, usually the endpoint of a very massive star imploding and generating a blast wave, a shock wave that generates extremely high energy electromagnetic radiation, which is what gamma rays are. Magnetars are extremely massive, highly magnetic stars where the cataclysm is extreme and the magnetic fields help accelerate particles to very high energies. And so some of the gamma ray bursts, the most powerful or luminous gamma ray bursts, appear to be associated with magnetars. But in every case, we're talking about the end point of a star's life, a stellar cataclysm. And the variations in the gamma-ray burst depend on whether that star, on the mass of that star, whether that star is isolated or in a binary system, and the immediate environment of the star, whether it's surrounded by material that might be swept up or heated by the cataclysm itself.
The next question is from Wendy, who sent an email asking, I've read various theories about, where did the Earth get its water? I've read various theories about asteroids, comets, and from outgassing of the solar nebula itself. What is the most accepted view?
There have been papers on this fairly recently. It seems like it's an old problem. Where did the Earth get its water? And so people have been trying to answer it for a few decades. There was a paper in Science magazine just a few weeks ago that presenting recent research. And at this point, it looks like the water of the Earth came from at least 3 sources, and each is important. So they all have, people are arguing about their relative contributions. Some fraction of it comes from what people call a late veneer theory, which is that the water get added to the Earth soon after its formation from the deposition of basically cometary material. So comets are frozen rocky snowballs, if you like, and they carry significant water in frozen form. And there are earlier phases of the solar system where these impacting objects could have brought a significant amount of water to the Earth, and that's the late veneer model. And that seems to be something that did occur, but it didn't account for all of the Earth's water. It also is likely that some of that water came from the inner solar system, from what we would commonly call the asteroid belt, or a little further out maybe, where there is, again, frozen. Most of those rocks are fairly dry, but many of them have a water content, and those rocks occasionally come on Earth crossing trajectories and so can carry water to the Earth. And then clearly a third component of the Earth's water came from the primordial material itself. It was associated, it was in hydrated minerals, that is minerals in the early Earth's geological material that involve water bound together with other molecules in chemical mineral form. And that, depending as the conditions of the Earth change in the interior, and these rocks undergo intense chemical processes driven by heat and pressure, that water can get liberated, and it can, of course, eventually percolate up through from the core mantle regions up towards the crust, where we might see it as the oceans of the Earth. And that's been the subject of the largest debate, because it's just very hard to diagnose the history of the early inner Earth, and it's also very hard to get samples of the Earth. We don't have samples of the mantle or the core of the Earth. All we have is some crust samples by digging holes a few kilometers deep. So people are still arguing about the relative contributions, but there are those 3.
The next question is from several people who have similar queries. Mary sent an email asking, I've read some speculation that the magnetic poles of the Earth may flip soon. I realize this has happened in the past, but what does the scientific community say about this, and what would be the impact on the Earth?
Yes, it's clear in the geological record, because we can look at the magnetic domains of minerals in the geological record, and when the record is laid down in strata, like from dust layers that get deposited periodically in a very fixed cycle, then you can do a stratigraphy of these dust layers, which contain magnetic minerals or magnetic aligned grains. And that allows us to see the flipping of the Earth's magnetic field every few tens of thousands of years. So it seems to be a phenomenon that has occurred through the history of the Earth. The precision of the measurement and the length of the measurement is not enough to see if that time scale is absolutely strictly periodic or has varied, but we think it's a standard phenomena. And it's associated with the dynamo mechanism within the Earth that generates the magnetic field. Eventually, and at some point, that magnetic field gets tangled because of the differential rotation of the Earth. Remember, the Earth has a liquid region in its interior. And at some point, the Earth magnetic field gets destroyed and reforms, reversing its polarity. So we see evidence of that. The full mechanism, not completely understood, it would be fair to say, but the geological record definitely shows signs that this has been going on for hundreds of thousands or rather millions of years.
Excellent. You sort of approached and covered the part of this next question. Earth has a magnetic field because its core rotates at different speeds. So why is that? Why is there a difference in those speeds? And why doesn't Mars have a magnetic field?
Um, it's differential rotation, which means part of it's due to the inertia of the rocky material. The Earth has an angular momentum due to its spin, but there's obviously viscous forces that apply between an outer region of the Earth and an inner region that might be liquid. The Sun is in a more extreme version of this because the Sun is just plasma, and so the equator region of the Sun rotates more rapidly than the polar region, and that, of course, causes the Sun's magnetic field to reverse every few decades, so that's the solar cycle, much more rapid. And the Earth, because the magnetic field is entrained in rock, and this differential rotation is a more subtle effect, the magnetic field reversal takes a lot longer to happen. In Mars, there is no liquid core. As far as we can tell, Mars it had geological activity in the past, but at the moment it does not have a liquid core, and so Mars cannot really long-term retain a magnetic field. So whatever magnetic field Mars might have had when it was geologically active has dissipated, and so we think at the moment Mars, like the Moon, has a very weak or absent magnetic field.
Thank you very much. The next question is from Gowrie, who's on with us live, who would like to know, is there life or could there be life underground on the Moon?
That's an interesting possibility, but because the reason we even would entertain that possibility is because we know there's frozen water or ice on the Moon, and especially in the polar regions, and especially in shadowed regions where it's actually on the surface. But underground, there are definitely going to be icy material. The Moon, however, it's unlikely that there's biology, even though water is a prerequisite for biology, because it's very unlikely that any of this water is in liquid form. It's possible, so we always leave the door a little open. The reason it's unlikely, however, is the Moon is a low mass object, and so there's insufficient pressure in the interior to make or internal radioactive heating to make that water liquid significantly. It's possible in localized regions that the conditions would be such as to allow water. So since the Moon has never had long-term persistent water on its surface the way we think Mars has, and since any interior water is extremely localized and probably doesn't last very long, the odds of biology existing anywhere on or in the Moon are very low.
All right, thank you very much. The next question is from Sudhanva, who is interested in sort of the age of the universe. And I think it's sort of similar, the question is sort of similar to the idea that distant stars that we can see now may already be gone. And so his question is, since we are so infinitesimally small compared to the universe, and our time is infinitesimally smaller than sort of universal or geologic time, is it possible the universe has already ended, kind of like those distant stars?
Well, we can look at this because we do observations. So when we look out in the universe, we look back in time. So looking out with large telescopes give us a reverse chronology of the history of the universe, and that's how we know the universe was hotter and denser in the past and started with something that we would call the Big Bang. If we look at the nearby universe, we're looking at the universe as it is now, or very recently, and we see a universe where the space-time is expanding at an accelerating rate, we think due to dark energy. And we see galaxies nearby that look very much like our galaxy. So there's no sign that the universe is about to end or has ended recently, because when we look at the nearby universe, we're looking at the recent past. And we can project into the future based on the conditions around us. And the conditions around us suggest that galaxies will persist, that the stars in them will continue to evolve, and new ones will form for, not forever, but for quite a long time, and that the universe will expand at an accelerating rate due to dark energy. And so we can play out that future expansion. So the universe will dissipate for sure, and the amount of matter or objects or galaxies that we can see with any telescope will gradually diminish until we can't see any. All we will be left with is Andromeda and Milky Way having merged. Just that one combined galaxy is all we could see. So that's sort of what the fate of the universe looks like. But this is a distant prospect. These are hundreds of millions of years before this happens.
We have a kind of a series of questions about dark matter, so we'll kind of take those in turn. The first question from Subham is simply, what is dark matter? Can you talk a little bit about what it is?
Dark matter was invoked by astronomers starting in the 1970s to explain how galaxies rotated, including the Milky Way. So what happens is when we look at the way spiral galaxies rotate, if galaxies were made of just the stars we see and they operated according to Newtonian gravity and Kepler's laws, the rotation speed of the stars should diminish as you go out in the spiral disk. Instead, we see the rotation speed staying constant right to the edge of the disk, and when we observe in gas, even beyond the stellar disk. And that's really only explicable if 5 or 6 times the amount of material we see in visible stars exist in a dark form. So the galaxies we see are embedded in large dark halos of material that's driving the speed of their rotation. After that work in the 60s, 70s, mostly the 70s, same observations were made of elliptical galaxies. The same effect is seen. They also seem to have dark halos driving their stellar motions. Essentially every galaxy studied appears to have some dark form of matter. So that's where the observations came from, building over a few decades. And then they were added to in the 80s and 90s by gravitational lensing experiments showing where gravity bends light, and it's all mass that bends the light, not just the visible stuff, the stuff we're made of. And again, dark matter dominates these lensing experiments by a factor of 5 or 6, so they're completely consistent with what we saw in the rotation of galaxies. So by the 1990s, this evidence was overwhelming that 5 or 6 times the amount of mass that we would see in normal particles, the stuff that all stars and galaxies are made of, the visible stuff, is outweighed by dark matter, and at the moment we don't know what that is.
The kind of a follow-up question to that is, are black holes a plausible candidate for dark matter? And if not, why not?
So could black holes be the dark matter or some component of it? Possibly. There's one door left open for that. But generally no, because the black holes that we are familiar with, the ones that are the remnants of massive stars after they die, it's very easy to see when massive stars die. There's a supernova, and then you have to have that before you get the black hole. So to postulate that all the dark matter we see, remember 5 or 6 times as the amount of normal stuff, were from massive stars that had died, we'd have seen enormous amounts of evidence of the precursors of these massive stars and their lives, especially of their supernova detonations, all the energy that produces, and then they leave behind the black holes. So you can hypothesize the black holes, but you don't see what happened before, and so that essentially rules that out. So we don't think they're normal black holes. And they're not massive black holes like we have at the center of the galaxies. Every galaxy has a black hole, but those black holes are about 1 part in 1,000 of the mass of the galaxy, so they definitely don't account for dark matter. They fall way, way short. The only window that's left open for black holes as dark matter is what are called primordial black holes, that are black holes that could have been produced early in the universe, just after the Big Bang, when space obviously was very dense and hot, and the mass density was enough that microscopic or small black holes could have formed. The very smallest of these black holes, if Hawking's theories are correct, would have evaporated, and so we would see no evidence of them. But there's a little window of small black holes that could have survived to the present day, and that could account for a significant fraction of the dark matter. Over time, people have narrowed the window for this by observations and trying to rule them out. There's only a very little window of mass available for primordial black holes to be any part of the dark matter, and so the door is open, but in the future we may actually rule out black holes entirely.
Excellent. The next question is from, those questions we covered were from Shannon and Alex, so thank you very much for asking those. The next question is from Janita, who would like to know, what is the latest with Beetlejuice? Why is it not exploding anymore? Are there any current studies, and what's the status?
Betelgeuse, of course, is being monitored extensively. It's a very bright supergiant star, and so easy to observe with ground-based telescopes and space-based observatories. And ever since it started behaving strangely, there have been people on it all the time. So we monitor it very carefully. It's pretty clear that Betelgeuse was involved in a sort of episode, a sort of spasmodic episode of releasing material into space, which included dusty material that was opaque and so darkened the star. And that's what led, and it's patchy as well. It's not fully surrounding the star. And so that's what led Betelgeuse to have this very erratic variation of its light, which some people initially interpreted as extraterrestrial intelligence or something like that. Well, no, it's a natural phenomena. People also wondered whether Betelgeuse was gearing up to die as a supernova and undergo violent detonation. The more recent observations just suggest that it underwent an episode where massive stars near the end of their lives do become unstable as their nuclear fuels change and they evolve to a new nuclear fuel, or the fuel starts to run out and the star reconfigures itself. And that seems to be what Betelgeuse has been doing, but there's not an indication that it's right at the very end of its life and so will die as a supernova anytime soon.
Thank you very much. The next question is from Rachit, who would like to know, why doesn't the moon spin?
And the moon did. When the moon formed, the moon spun. It shared the angular momentum of the Earth at some point, and since in the hypothesis that the moon formed from a collision of the Earth with a Mars-sized objects, the moon sort of got some fraction of the Earth's angular momentum and had some angular momentum of the object that impacted with the Earth. So the moon had a shared amount of angular momentum from its original object and the thing it hit, the Earth. So the moon was originally spinning, but as the moon formed and stabilized and circularized its orbit, it was such a large moon compared to the mass of the planet that it orbited that the tidal forces essentially locked it to face one side to the planet. And that's the case of all relatively large moons near planets, or large planets near the sun. Mercury is tidally locked for the same reason. So it's because the tidal force relates to the stretching or the gravity between the near side and the far side of a moon or a planet. And when that stretching or tidal force is large compared to the overall force that keeps the planet in orbit, or the moon in orbit, then you have tidal locking. And so the moon has been tidally locked since pretty near the beginning, and will stay that way for quite a while.
The next question is from Parth Sarda, who's on with us live. Who sent an email. What happens to objects at 0 degrees Kelvin? Some people say an object loses all of its energy, but that wouldn't seem to obey our physical laws.
Well, we cannot absolutely create 0 degree, 0 energy, 0 temperature. The closest, although lab experiments have gone pretty close to this, I think the record for low temperature in a lab physics situation is less than a billionth of a Kelvin, so pretty amazingly cold. And these are essentially atom traps, where you trap an atom or a small number of atoms with lasers or acoustic waves and essentially freeze the motion. And therefore, since motion reflects kinetic energy, which relates to temperature, you can create the equivalent of a very low temperature. The reason it is true that you cannot create absolute 0 temperature because the vacuum of space has a small amount of quantum energy, the Planck constant divided by 2, essentially, energy. That's a result of quantum theory, that the vacuum has a small amount of residual energy just due to quantum effects, fluctuations of energy in the vacuum, essentially. So for that reason, according to quantum theory, yes, it's impossible to create absolute 0 temperature, but we've got very close.
And kind of a follow-up to that is, are temperatures below absolute zero or 0 degrees Kelvin possible?
No, absolute zero is a limit, and it's an asymptotic limit, which is to say we can approach it but never reach it because of quantum effects. But there is no meaning to negative temperature.
The next question is from Lily, who would like to know, and you can expand on this a little bit. She would like to know if you have a favorite constellation, but I thought maybe you could just talk about if you have any favorite astronomical objects or phenomena.
Yes, I mean, just a personal favorite constellation probably would be Orion because it's a great winter constellation and it looks great from Tucson and our dark skies. And it's, if you have binoculars, you know, the Orion Nebula looks pretty great. There's a lot of active star formation in the Orion region, so it's a pretty rich area of the sky. So as a constellation, that's probably my favorite. And favorite objects, you know, I work on active galaxies in my research, so I tend to like quasars and active galaxies. These are supermassive black holes that are, when they're in an active phase of accreting gas and eating up stars and dust, they shine far brighter, sometimes hundreds or thousands of times brighter than the galaxy that contains them. Luminosities of 1,000 trillion suns, which is an incredible number. So those, as a class of objects, those are my favorite objects because they are so extreme in their properties.
The next question is from one of our live viewers. Elements lighter than iron are made inside stars, but where are the elements that are heavier than iron produced?
Beyond iron, which is the most stable element, so it does not occur readily by fusion. It's a sort of endpoint of the fusion chain because you have to put energy into an iron nucleus to fuse it to a higher atomic number, whereas as opposed to releasing binding energy, which happens all the way up to iron. So something extra has to go on to get past iron, and that's why stars essentially stop there. And the two places where that can happen and where you get heavier elements are in the violent detonation of the death of a massive star in a supernova explosion, where the extra energy needed to go beyond iron and all the way up the periodic table is from the blast wave, which reaches instantaneous temperatures of a few billion degrees Kelvin. So that's one place. And the other place is, and that's called, in nucleosynthesis terms, that's called the R process, R for rapid, because it happens very quickly, in seconds basically. There's also an S process in nucleosynthesis, which is for slow, and that occurs in the envelopes of evolved stars. And it's a more subtle way of generating heavy elements. Basically, there are free neutrons in these hot envelopes of massive evolved stars, and those neutrons, because they have no electrical charge, can penetrate an atomic nucleus, like an iron nucleus, and so they can bump it up the periodic table. They will undergo a transmutation, sort of inverse of beta decay, which is when free neutron decays. And so by adding neutrons to an atomic nucleus, you can nudge it up the periodic table and also sequentially get all the way up to the heaviest elements.
All right, I've been kind of waiting till the middle of the session to discuss this. We have several people who would like you to discuss the recent discovery of phosphine in Venus's atmosphere. Can you explain the discovery a little bit? And what is your take on the possibility of life on Venus?
So the discovery is of a molecule which on the Earth is implicated in biology, which is to say we don't actually know the full process by which phosphine is used in biological organisms, microbes typically, but we find it's found associated with microbes under the surface of the Earth typically. So it seems to have a biological origin on the Earth, and therefore if we see it elsewhere, it's natural to assume a biological origin. The caveat on that is that you can make phosphine under sufficient conditions of temperature and pressure, given its chemical ingredients. But this was an observation of phosphine in the mid-level atmosphere of Venus, which is not a very extreme condition of temperature and pressure. So that doesn't explain it. And so the speculation is that there are microbial organisms circulating within the atmosphere of Venus. The question of how they could evolve or get there or sustain themselves in a gaseous environment is completely up in the air, and really nobody has a plausible explanation. But the measurement of the phosphine is correct. They did see that molecule, and on Earth it's associated with biology, so it certainly makes for an interesting hypothesis that there's life of some kind in the atmosphere of Venus. And it's led to activation of several missions that had sort of been proposed years ago and were on hold in favor of other missions to go to Venus, to send probes down through the atmosphere and make measurements, and some even to survive to the surface and make measurements there. And so we'll learn a lot more when we send a space probe rather than trying to use telescopic observations, which is a little indirect.
Thank you very much. The next question is from one from our live viewers. Moo Meow would like to know if scientists could make a large telescope using water instead of glass.
Water, very hard to do. First of all, water is not reflective enough. You actually want a very reflective material for a telescope. So water, it absorbs light and it transmits light and refracts light, but it doesn't reflect light very well. So water is not a good material. Ice, of course, is more reflective, but it's extremely difficult to make an ice surface smooth. So water, no. The liquid that has been used for telescopes and even some significant size telescopes is mercury. So the mercury, that very rare metal that's liquid at room temperature and normal pressure, is quite highly reflective, as you probably know if you've seen mercury. It's highly toxic and fairly dangerous, of course, so you don't want to come into contact with it routinely. But people started in the 1970s, actually, in the University of Montreal, I think was the first place, to make rotating liquid mercury mirror telescopes. And they've now got up to several meters. I think 3 or 4 meters is the biggest, and proposals exist for 6 or 10 meter liquid mercury telescopes. They have a big limitation, which is, of course, the liquid mercury is spun to create a parabolic surface, and that's fine, but it only lets you observe a strip of the sky straight overhead. You cannot steer this telescope around the sky. Now, if it's a big telescope and can see very deep, that's not a limitation. You can do interesting surveys looking at a strip straight overhead. The advantage, of course, of the liquid mercury mirror is that if the mercury gets contaminated over time, you can just take it out and filter it and put it back in again. So refurbishing your mirror when it's made of mercury is actually fairly easy, bearing in mind you have to handle it extremely carefully. And also, mercury, and since it wouldn't be a very thick layer of mercury, it would be on a substrate, is not incredibly expensive. So it's actually a fairly cheap way to make a fairly large telescope. So liquid mercury rather than water is the way people have actually made some fairly large telescopes in the past, and even some bigger ones planned.
A couple of people have pointed out regarding our earlier moon question, I don't remember if you addressed this, that the moon technically does spin on its axis. It just spins at the same rate that the Earth spins. I don't know if we specifically addressed that in the question, but yes, that is correct for those of you pointing that out. To clarify, but again, from our perspective, the question, I'm sure, was why does it always face the same part of the moon? So Luis would like to know, why is it that elliptical galaxies are not rotating like spiral galaxies? Do they have less dark matter, or do they have black holes in the center? How are these things different?
Elliptical galaxies, the speculation as to their relatively low rotation or angular momentum is that it's due to initial conditions. Elliptical galaxies do have black holes. Basically, all galaxies seem to have black holes, and the black hole mass just goes with the mass of old stars in the galaxy. And since elliptical galaxies are almost entirely old stars, they have the biggest black holes that we know of. M87 is a good example. The black hole that was imaged by the Event Horizon Telescope a year or so ago is a 6 billion solar mass black hole in the center of a giant elliptical. So they do have black holes. They do have dark matter, and they have similar ratios of dark matter to normal matter as other galaxies, spiral galaxies or irregulars. So they're not special in that way. The initial condition part just implies that when the cloud, the large and nebulous gas cloud that collapsed by gravity to produce a stellar system, if it initially had very low angular momentum, then the gas probably collapsed almost spherically and formed stars quickly in one generation. And so you would expect, and once the stars form, of course, they take up elliptical orbits around the center of mass of the system. They don't collide with each other because stars are so small compared to the space they occupy. And so you end up with a galaxy that retains its roughly symmetric distribution, whose stars are engaged in elliptical orbits, and whose stars all formed almost at the same time early in the history of the galaxy, and so in many cases they're very old, and indeed some of the oldest stars we see in the universe are in elliptical galaxies. So it seems to be down to their initial conditions. Now, a slight caveat to that is we think that by simulations, we think that when spiral galaxies merge, like two spirals like our own, or two or more spiral galaxies or small galaxies merge, they can circularize the orbits and end up with a roughly elliptical looking system where the ages of the stars may not be very old. So it seems like a second path to an elliptical galaxy is by a series of mergers.
The next question is from Ignacio, who's on with us live. How does general relativity explain the 9.8 meters per second acceleration of gravity towards the Earth?
Well, general relativity at its heart is saying that mass and energy curve space and time, and those things are hyphenated in general relativity. Mass, energy are a connected concept, and space-time is a connected concept. So in the idea of general relativity, the Earth is a massive object and it's distorting space-time, and when objects fall towards the Earth, they're just taking essentially the shortest path through space-time to the center of the Earth, where the center of mass is. And in any other part of the universe, they would do the same. An object would do the same thing. And these trajectories are standard in general relativity. You look at the trajectory of an object through space-time, and it's defined by the gravitational potential. And the gravitational potential incorporates the curvature of space-time.
Excellent, thank you very much. There is one of our live viewers who would like to know if Hawking radiation really exists, and perhaps you can talk about what Hawking radiation is and whether we've ever detected it.
Hawking radiation is the hypothesized effect of the fact that black holes are not eternal. Hawking hypothesized in the 1970s and early 80s a mechanism whereby near the event horizon of a black hole, a small amount of net radiation can be produced, essentially drawn from the vacuum of space, because we know the vacuum can create particle-antiparticle pairs. And so you're essentially drawing on the vacuum energy to produce radiation, which then leaves the black hole's event horizon. And the effect of that, of course, is the black holes have a temperature, and the prediction of Hawking radiation is a stellar mass black hole will have a temperature of a very small fraction of a Kelvin, about a billionth of a Kelvin, I think. And also that there's a net loss of mass, because again, mass and energy are equivalent, so the black hole equivalently is evaporating. And so those are two predictions together. They're coupled predictions of Hawking's theory. Neither have been confirmed, and it's actually not possible even to test them at the moment, because the rate of evaporation is so low and our mass measurements of black holes so crude that we couldn't measure that from year to year. And the temperature of Hawking radiation is also so low, so close to absolute zero, and black holes are often in chaotic, confusing regions where particles are being accelerated and there's an accretion disk, that we couldn't detect Hawking radiation either. So there's not even a real prospect at the moment of how we would prove Hawking was right.
Thank you very much. The next question is from one of our live viewers, and that is on what factors does the size and mass of a star depend, and what how does this determine its characteristics during formation?
Formation of stars is a complex, chaotic, messy process. Stars do not form singly, typically. They form in large aggregations in large regions of space where gas is condensing and collapsing due to gravity, and there's dust mixed in there. So stars form usually in groups or concentrations or clusters. And the nature of this is fragmentation. So there's a process called fragmentation where a large cloud will have various subregions within it that go into gravitational freefall, and they form individual young stars or protostars. And that'll be happening simultaneously at various places through the cloud. The nature of subfragmentation is it's a hierarchical process, and that typically means that there will be many more small fragmentation regions and therefore small mass stars than large mass stars. And so the process of formation out of a large cloud should naturally lead to more low mass stars than high mass stars, and that's what we observe. Dwarf stars, red dwarfs, are much more common than stars like the Sun, which are much more common than more massive stars. So that checks out, and we have simulations to sort of show that. So the mass is what drives the evolution of a star. Once you know what the star's mass is, you can say everything else about it. You can make a model given its fusion reactions for its size, its temperature, its luminosity. So really, when we look at star formation and try and understand it, what matters really is the mass of the star that forms and how many stars of different masses form. Everything else is determined by stellar astrophysics after that.
Thank you very much. There was a clarification on one of our earlier questions. Apparently, the questioner who asked about the water telescope was asking if water could technically be used to make a refracting telescope. So perhaps you could address whether it could be used to make a refracting telescope, and then talk about a little bit why we don't use refracting telescopes for professional astronomy anymore.
Right. So, I mean, it's a kind of bizarre thought, but yes, you could make a refracting telescope with water. You could you make a sort of water lens, if you like. You could fill a lens-shaped rigid container with water and use that as the liquid medium, and then indeed, if it had the right shape, it would refract light and focus light. So you could make a refracting telescope with water lenses as opposed to glass lenses. But there's no real advantage to that, because the problem with refractors as they get bigger is the rigidity of the optics. And glass itself is not completely rigid. It very slowly flows and morphs under varying conditions of temperature and pressure. And a water-filled lens would probably even have a worse problem of that, keeping it rigid. So I think for that reason, although you absolutely could make a water lens telescope, it's not going to improve on refractors in general, and so astronomers have pretty much given up on refracting telescopes for doing research.
The next question is from Jim McLeod, who's on with us live, who would like to know if you could suggest a couple of websites or periodicals that would help students of astronomy keep up with breaking news and research.
Well, sure. I mean, it's a kind of chaotic website, but space.com is pretty good for astronomy and for also space science, planetary science, what's going on in the space program. So it's a way to find a lot of things. There's also an online periodical called Science News Daily, and you can set up a feed. It does science across the board, of course, but you can set up like an RSS feed or a news feed to just pick out the astronomy articles, and I get that feed, and typically there's a handful, sometimes 5 or 6 articles every day, and they give links essentially to press releases that come out of major universities and research institutes. So you can read a nice summary in popular language of the result, and at the bottom there's always a link to the paper itself, the research paper, on the archive or at the journal. So that's a nice way to get, really current and significant research results. So there are a number of ways. Those are two, and there are other science news sites which include significant amounts of astronomy. The major magazines, Sky and Telescope and Astronomy magazine, they also include current events and news in astronomy, but typically there are feature articles, so it's only 1 or 2 a month.
The next question is from Hamza Akhtar.
You cut out, Matthew.
Oh, I'm so sorry about that. The next question is from Hamza Akhtar, who is sort of responding to one of the earlier discussions about Venus. So we're associating life with the existence of liquid water and organic molecules, but isn't it possible that life could be sustained with either mysterious or inorganic molecules and reactions?
It is possible. So we should always hold open the possibility of strange forms of life, since we only know of one form of biology. Everything on the earth that is living is related to everything else because it's the same genetic code, it's the same origination 4 billion years ago. So we should be very cautious about ruling things out. Now, carbon-based chemistry and biochemistry is a very good basis for biology because carbon forms strong, stable bonds and makes molecules of essentially infinite length. And so for storing information, which is a requirement for life and the genetic operations, carbon-based chemistry is best. So to do biology without carbon seems like a stretch. Silicon is not nearly as good. It's in the same column of the periodic table, but the stability of silicon-based molecules is not as good. The complexity of molecules you can make with silicon-based chemistry is not as good. So various alternatives don't look as good. It's not necessary to have water as the solvent or the medium for life. If you assume it needs a liquid medium, you could have ethane, methane, as in the oceans and lakes on Titan. That would be an exotic possibility for life. You could use glycol. So there are other molecules that are stable and fairly inert and that could be a medium for holding biochemistry of different kinds. The problem is we don't really know how to make a good hypothesis for what the alternative is. So when we're talking about an alien environment like the atmosphere of Venus, we know what the chemical ingredients of the Venusian atmosphere are, and if you take all those ingredients and do lab experiments or simulations, you don't get biochemistry out. So again, nobody knows a pathway by which Venus could have microbes in its atmosphere. That doesn't mean that it couldn't happen in a way we haven't anticipated, but at the moment we're just very ignorant about biology, anything different from the Earth form.
Bob Ravi would like to know what basic preparations are required to live on the moon, since NASA is planning missions to the moon and to stay for a while.
The preparations are going to be sufficient infrastructure. Well, I think there'll be a safety requirement. So any colonists or people visiting the moon for any period of time will need to be able to leave quickly if something goes wrong. And so they'll have sitting at the ready their rocket or their escape vehicle to come back to the Earth. So that's a very basic requirement, a way to get home quickly if you had to. The other requirement is a sort of stable and secure living environment. And what that means is essentially a hardened dome made of very impervious material, because you have to worry about micrometeorite hits. You have to protect the occupants from radiation, from cosmic rays, and from high energy particles, electromagnetic radiation. So you've got to have a hardened structure, and you can actually make such a structure from lunar regolith, the lunar soil, using electrochemical processes. So you don't have to bring out a lot of expensive or heavy materials from the Earth, which would make it very expensive to do the mission. So you need a secure environment. You obviously need a source of oxygen and air to breathe, then inert nitrogen, and then the active oxygen that's an essential ingredient for humans, and some way to regulate that very carefully. So as we know from the biosphere experiment, which happened only a few miles north of where I'm right now, it's very hard to make a sealed environment and keep the stability of the atmosphere long term when there are, say, plants and humans in that environment. So stable atmosphere, a source of oxygen to replenish, and a source of water, of course. And again, water can be obtained from hydrated minerals in the lunar soil, so you hopefully would not even need to bring the water out. So I'd say water, air, a hardened structure, and a way to escape are the main requirements for us to live on the moon for any length of time.
We have had this question before, and we have the Divine Wanderer who's asking it today, who would like to know your thoughts on, is it any way possible that space-time and consciousness are connected, or could the universe be some kind of like overarching consciousness or conscious entity?
So I'm not sure I can talk about the space-time part. Space-time is just a construct through general relativity for the universe we occupy, just describing the space-time. But as far as the universe as a potential conscious entity, I can speak briefly to that, and mostly to say that I don't think it's a plausible hypothesis. And that's not because I have any evidence against it, it's just that I don't have any evidence for it. So consciousness, of course, is something we don't understand, even within the context of human beings or potentially other animals that we think might have self-awareness or consciousness that we share the planet with. So given that we don't understand human consciousness, our own consciousness, it's very hard to extrapolate it to an entirely different realm. Over, consciousness does require some degree of organization or self-organization. The brain is a highly complex, without being overly materialistic and connecting one-to-one consciousness and the human brain. The brain is clearly implicated in consciousness, and the brain is a highly complex electrochemical network with trillions of neurons and 1,000 times more connections between those neurons. The universe is not organized in any way like that. So even though the universe is vast and contains billions, trillions, and trillions of stars and hundreds of billions of galaxies, there's no overt or even subtle organization to the universe that we found. And we've looked at it pretty carefully with big telescopes. So the universe does not show any signs of grand scale organization. There are patterns in the universe. There are structures of clusters and superclusters and voids and filaments, and so we've seen structure in the universe, but it's not of a kind that suggests overall organization. So it's not clear how you would get something that we think looks like consciousness out of what we see the universe as with our big telescopes.
Okay, it is the end of our time for today, and we will take one more question, and then we will wrap up. So the next question, there are several people with this question or similar questions, and it's generally, do you think that life exists in the universe elsewhere? But also, could you address the idea that does NASA have proof of aliens, or is that just a myth?
Well, I'll treat this as two questions separately, or briefly answer each. The question of life in the universe is a wide open question, and the number of exoplanets and the number that are habitable, the widespread availability of the chemical ingredients for life across the universe, and the sheer amount of time and real estate of habitable worlds suggest that it's unlikely that biology is unique to this planet. So without any direct evidence, astronomers are operating under the assumption that it's fairly likely that there's life beyond Earth somewhere, and probably many places. For the second question of alien life and whether it exists and whether we already know it and NASA found it and maybe kept it secret, that's edging into the conspiracy theory area. I don't think astronomers rule out the possibility of intelligent life elsewhere because they think life itself, or biology of some form, probably microbial for the most part, is quite likely elsewhere. So it would be illogical to rule out intelligent life, since intelligent life evolved from microbial life on this planet and might do elsewhere. So, but it could be a lot rarer than microbial life. So logically, it could exist, but also logically, however rare or common microbial life is, intelligent life is rarer, and it might be an awful lot rarer. And it might be so rare that what happened in the Earth was a fluke or a thing that doesn't happen very often at all. So that's the science behind what we can say about intelligent life in the universe. And then asking whether we've already detected it, we just have to hold the evidence for that, whatever evidence people want to put forward, to a very high bar. And I think the bar is set suitably high that no evidence that's been claimed by anyone I've seen or that's been published and shared gives any sign that intelligent life has been found up to this point. And NASA simply would not be able to keep such a thing secret, nor would they be inclined to. So my view and the view of most of my colleagues is that no, we haven't found intelligent life in the universe yet, but it could quite possibly exist. So thanks for all your questions. Biology, astrobiology to cosmology as usual, and the Earth in between. So good questions, and we'll be back with you next week, and we'll announce the next 2 sessions soon. Okay, thanks everyone. Thanks Matthew for facilitating, and Alexander behind the scenes as always. Bye.
And thank you very much, Chris. The last thing I wanted to mention to everybody is that we are going to be trying out some additional live streaming opportunities I'll be talking about amateur astronomy, and we have some students that will be talking about astronomy news. And if you are interested in checking out those other live streaming opportunities, make sure that you get on our Discord server, which is in the description at the bottom of this video, or check out the emails from our courses when they come out. So we will let you know as those are available.